So far we've covered two examples that belong to gravitational theory, to attraction among masses. So it's about time that we apply that knowledge of potential energy to the attraction between electrons and the nucleus of the atom. So again, we will see this equation in a minute, but the energy of two charges in this case is the product of the two charges divided by the distance among them. We know that in quantum mechanics this may be a little bit more complicated, but the basics are still apply. So when we think about the 1s orbital and the 2s orbital, one being larger and the other one being smaller, so remember the 1s is smaller, this one is larger, that means this one is closer to the nucleus, closer to nucleus, and this one is farther from nucleus. How does the potential energy change? Well, first of all, think of that the zero potential energy will be when R is infinite. In other words, when you kick the electron out of orbit, if you will, when you have a free electron, so the energy can only be negative, of course, provided that the charges have opposites, so Q could be the charge of the nucleus, which is positive, right? Charge of nucleus is positive, and the other Q is the charge of electrons, which is negative. So provided that the interacting particles are a positive and a negative charge, the energy is always negative. Okay. So here you have your s orbital. Because it's closer to the nucleus, this R will be smaller. That means this energy will be more negative. In other words, it will have a lower potential, and the 2s will have a less negative and a closer to zero energy. How does that look like using the graph that we've been using so far? Well, let me show you that we're still applying the same rule, okay, and k is just a constant, but how does it change if I change the charge of the nucleus? If the charge of the nucleus now changes, let's remember, I don't know how to spell nucleus, remember what we said in the example between Earth versus the Moon, because the fact of the Earth has a larger mass, in this case the atom of oxygen has a more positive nucleus, actually has 8 protons, so it's a 8 plus. Lithium only has 3 protons, so it's a 3 plus. Because of that, the electrons in the 1s orbital will already be in a more negative potential. On the other hand, for lithium, this lithium would be the Moon and oxygen would be Earth. The fact that the nucleus has a less positive charge, it can attract less the electrons, therefore the energy of the orbitals will be closer to zero. Okay, and again, this would be the plot, and please make sure you understand what we're saying, like that the closer the electron is to the nucleus, the more negative the energy and more stable the electron is. Okay, and notice that for lithium, the attraction is smaller, therefore the same that for the Moon, this would be when we said it could be the Moon, and the oxygen would be Earth. Okay, the change and the attraction for lithium is smaller. Okay, and of course what we are trying to show here is that the more positive the nucleus is, like oxygen, the more negative the energy is, and the more stable the electrons are. Okay, so let's go through this again. The more positive the electrons, the more positive the nucleus, what happens? Well, the energy will be more negative. That means that the attraction increases. That means that the stability increases. And it's harder to remove the electrons because it's down in terms of energy. That means the ionization energy will be larger. So now we know why the ionization energy of oxygen is larger. It's because it has a more positive nucleus than lithium. Okay. So let's just run a simple questions. Let's see if that makes some sense. So the 1s orbital has a higher or lower potential than the 2s orbital. If you remember what we said, the 1s would be like the apple falling on the floor, and the 2s would be, this is your zero energy out of orbit. The 1s has a lower potential energy, more negative you will, than the 2s. Now, the 1s has a more or less negative. Well, the 1s has a more negative potential. The third question, the 1s orbital is more or less stable. We just said here, right, the larger the stability is related to attraction, to a lower energy. In other words, the apple is more stable on the floor than on the tree. This is why when you let it go, it evolves to the floor. An electron here, if it has room and doesn't violate Pauli's principle, in other words, if there isn't already 2 electrons here, it will fall down to the 1s, and this energy will be a photon of light. Right? So the 1s orbital is more stable. This is why electrons, unless there's already some electrons in the 1s, will move to 1s. The closer or the farther the orbital is from the nucleus, the lower its energy. We said right here, right, that we didn't say it here. So that was the more positive, but the same can be said that the closer to nucleus, or if you will, the lower the distance, the lower the energy and the higher the attraction. So these two influences have the same effect on energy, attraction, stability. So the closer the orbital is from the nucleus, the lower its energy. Therefore, it will be harder to remove. Now, the 2s orbitals of carbon is more or less attracted by nucleus than the 2s of oxygen. Well, oxygen has a more positive nucleus. So because this has a more positive nucleus, it'll be attracted more. Let's remember here, the more positive the nucleus, the lower the energy, the higher the attraction, the higher the stability, the more difficult it will be to remove it. So the 2s of carbon will be less attracted by the nucleus because the charge is smaller. Carbon is a +6 charge in the nucleus, oxygen is a +8, it has 8 protons. Question number 6. An electron in the 2s orbital of carbon has more or less potential than an electron in the 2s. Whoops, they should say oxygen. I apologize. Right? Otherwise, right? We're just comparing the 2s orbital of carbon. So the 2s orbital of carbon is less attracted, so that the energy is closer to 0. Okay, let's just make sure. Right? This would be, in this case, it's lithium. But the same could be applied for carbon. It's closer to 0. Therefore, an electron in the 2s orbital will have more potential energy. It's closer to 0. It's less negative. Okay. Now, question number 7. The potential energy change when an electron falls from 2p2s in oxygen is higher or lower? Well, let's remember I'm just going to write the same thing. So this would be our 0 potential, this would be the 2s and 2p, and making exaggerated, this is the 2s and the 2p. In oxygen you have a +8, that means you're attracting the electrons more, and this is for carbon, you have a +6, you're attracting the electrons less. Okay, and this change, and I should have made scale, this would be our moon, and the carbon would be our moon, oxygen would be our Earth, because the charge of the nucleus changes also the relative stability. In the case of oxygen, the potential energy change will be higher. Alright, so expect, for example, if there's an electron moving from the 2s to 2p on oxygen, that the light associated to this transition will have a higher energy and a higher frequency and a lower wavelength. Alright, so Does it take more or less energy to remove electron from the 2s than from the 2p? Well, the 2s is more negative, so the energy necessary to ionize your electron is higher. So it takes more energy to remove an electron from the 2s than from the 2p. Does it take more or less energy to remove an electron from the 2s in carbon or from the 2s in oxygen? We said that because oxygen has a more positive charge, the electrons in the 2s have a lower energy, more negative. The required energy for oxygen will be higher. The required energy to remove the electron from the 2s will be smaller. So there will be less energy in carbon than in oxygen. The next step will be to apply these concepts to when there is more than one electron on the same shell, so we can talk about shielding and effective nuclear charge.